For nearly a century, one of the most puzzling mysteries in physics has challenged our understanding of reality itself. It began with Albert Einstein's deep skepticism about a strange quantum phenomenon. Einstein famously dismissed quantum entanglement as spooky action at a distance. He couldn't accept that particles could somehow influence each other instantaneously, no matter how far apart they were separated. The idea seemed impossible. How could measuring one particle immediately affect another particle on the opposite side of the universe? Einstein believed there had to be hidden variables, some unknown mechanism that could explain these mysterious correlations. For decades, this remained one of physics' greatest unsolved puzzles. Then, between 2015 and 2022, researchers at MIT conducted a series of groundbreaking experiments that would finally settle this century-old debate. These experiments didn't just prove that quantum entanglement is real. They demonstrated that Einstein's spooky action at a distance is not only possible, but it's one of the fundamental features of our universe. Today, we'll explore how MIT's revolutionary experiments confirmed what Einstein couldn't accept, and discover why this breakthrough is reshaping our understanding of reality and opening doors to technologies that once seemed like science fiction. Imagine you have two magical coins that share a mysterious connection. When you flip one coin and it lands heads, the other coin, no matter how far away, instantly becomes tails. This is essentially what quantum entanglement is like. Quantum entanglement occurs when two or more particles become linked in such a fundamental way that they share the same quantum fate. This connection persists regardless of the distance separating them. When we measure a property of one entangled particle, such as its spin direction, we instantly know the corresponding property of its partner particle, even if it's on the other side of the universe. This phenomenon was so strange that Albert Einstein famously dismissed it as spooky action at a distance. He couldn't believe that nature would allow such instantaneous connections between distant objects. To understand how remarkable this is, imagine two dancers who have never met, separated by thousands of miles. Yet when one dancer spins left, the other instantly spins right, perfectly synchronized without any communication between them. Quantum entanglement has three key properties. First, the particles share correlated properties. Second, measuring one particle instantly affects its partner. And third, this connection works regardless of distance, whether the particles are inches or light years apart. Einstein had a fundamental problem with quantum entanglement. The idea that measuring one particle could instantly affect another particle, no matter how far away, seemed to violate everything he understood about the physical world. Einstein believed in something called local realism, a principle that seemed so obvious and fundamental that questioning it felt like questioning reality itself. Imagine Alice and Bob are 1,000 kilometers apart. In our everyday experience, if Alice wants to influence Bob instantly, it seems impossible. Any signal or influence must travel through space, and nothing travels faster than light. This is the principle of locality. Any influence Alice has on Bob must travel through space at the speed of light or slower. For our 1,000-kilometer distance, even light takes over 3 milliseconds to travel between them. The second part of Einstein's belief was realism. This means that objects have definite, well-defined properties, whether we observe them or not. A coin, for example, has a specific weight, is made of a particular metal, and is either showing heads or tails, even when no one is looking at it. Here was Einstein's dilemma with quantum entanglement. According to quantum mechanics, when you measure particle A, you instantly determine the state of particle B, no matter how far apart they are. This seemed to violate both locality and realism simultaneously. It violated locality because the influence appeared to be instantaneous, faster than light. It violated realism because the particles seemed to have no definite properties until measured. Einstein refused to accept that nature could work this way. Instead, Einstein believed there must be hidden variables, properties we simply hadn't discovered yet, that would explain these correlations without violating the fundamental principles of locality and realism. He was convinced that quantum mechanics was incomplete, not that reality itself was strange. In 1935, three brilliant physicists came together to challenge the very foundations of quantum mechanics through a thought experiment that would become known as the EPR paradox. Albert Einstein, working with Boris Podolsky and Nathan Rosen, designed a thought experiment to expose what they believed was a fundamental flaw in quantum mechanics. Imagine two particles that become entangled, sharing a mysterious quantum connection. According to quantum mechanics, measuring one particle instantly affects the other, no matter how far apart they are. Now, let's separate these particles across vast distances, perhaps to opposite ends of the galaxy. Quantum mechanics says they remain connected. Einstein, Podolsky, and Rosen argued that this was impossible. They believed there must be some hidden mechanism, some unknown property or signal that explains how the particles stay connected. Their reasoning was logical. If quantum mechanics claims particles can instantly affect each other across any distance, this would require faster-than-light communication, which Einstein's relativity forbids. Therefore, they concluded there must be hidden variables, unknown properties that the particles carry with them from the moment of entanglement. This would mean quantum mechanics is incomplete. According to EPR, particles would carry hidden properties from the moment they're created. Like coins that are already heads or tails before you flip them, these properties would explain the correlations without any spooky action at a distance. This became known as the EPR paradox, a challenge that would haunt quantum physics for decades. Either quantum mechanics was incomplete, or nature truly allowed for instantaneous connections across space. The question remained, who was right? In the 1960s, a brilliant physicist named John Bell was grappling with the same questions that had puzzled Einstein. Was quantum entanglement real, or were there hidden variables we simply couldn't detect? Bell realized that this wasn't just a philosophical debate. It was a scientific question that could be answered with mathematics and experiments. He devised what would become known as Bell's theorem. Bell's breakthrough was creating mathematical inequalities, specific numerical limits that any theory based on local hidden variables must satisfy. Think of Bell's inequalities like a speed limit for correlations. If hidden variables exist locally, then the correlations between entangled particles must stay below a certain mathematical limit. Local hidden variable theories predict that a specific mathematical combination of correlations, called S, cannot exceed the value of 2. This is Bell's inequality. But quantum mechanics makes a different prediction. It says that entangled particles can achieve correlations up to 2 times the square root of 2, which is approximately 2.83. This difference is crucial. If experiments measure correlations greater than 2, then local hidden variables cannot explain the results, and quantum entanglement must be real. Bell's theorem provided something that had never existed before: a clear mathematical way to distinguish between Einstein's hidden variable theory and quantum mechanics through experiment. The experimental setup is elegant in its simplicity. Create entangled particles, send them to separate detectors, measure their properties at different angles, and calculate the correlations. If the measured correlations violate Bell's inequalities, if they exceed the value of 2, then Einstein's local hidden variables cannot exist, and quantum entanglement is confirmed as a fundamental feature of reality. Between 2015 and 2022, MIT researchers embarked on an ambitious mission to definitively prove quantum entanglement. Their sophisticated laboratory became the stage for some of the most precise quantum experiments ever conducted. The breakthrough experiments spanned 7 crucial years, with each phase building upon previous discoveries. This timeline represents a systematic approach to closing every possible loophole that skeptics could exploit. The experimental setup was elegantly simple, yet incredibly sophisticated. A laser beam strikes a special crystal, creating pairs of entangled photons that travel to separate detectors. The magic happens in the measurement precision. Watch as entangled photons are created and travel to their detectors. These particles remain mysteriously connected, no matter how far apart they travel. The detectors must capture and measure them with unprecedented accuracy. The key breakthrough was achieving measurement precision exceeding 99.9% accuracy. This level of precision was made possible by advanced photon detection systems that could capture the faintest quantum signals with extraordinary reliability. These experiments were specifically designed to close the loopholes that had plagued previous studies. The detection loophole was closed by achieving near-perfect detector efficiency. The locality loophole was addressed by ensuring measurements happened faster than light could travel between detectors. By 2022, MIT had created the most rigorous test of Bell's inequalities ever conducted. Their experiments didn't just confirm quantum entanglement, they eliminated every reasonable doubt that skeptics could raise about the phenomenon. For decades, quantum entanglement experiments faced a persistent problem. Critics could always point to potential loopholes, weaknesses in the experimental design that might explain away the mysterious correlations without invoking true quantum entanglement. MIT's breakthrough experiments were designed to be completely loophole-free by addressing three critical vulnerabilities that had plagued earlier studies. Think of these as security flaws that needed to be patched to make the results absolutely convincing. The detection loophole was perhaps the most obvious weakness. Early detectors were inefficient, catching only a fraction of the particles produced. Skeptics argued that maybe the correlations only appeared in the subset of particles that were actually detected, while the missed particles might tell a different story. MIT solved this by achieving detection efficiencies above 96%. Their advanced photon detectors caught nearly every particle, leaving no room for the detection loophole argument. This was like upgrading from a leaky bucket to a nearly perfect container. The locality loophole was more subtle, but equally important. If the measurement settings at two detectors were chosen too close in time or space, information could theoretically travel between them at light speed, creating artificial correlations that mimic entanglement. MIT closed this loophole by ensuring that measurement choices were made so quickly and at such distances that even light couldn't travel between the detectors in time to influence the results. They created what physicists call space-like separated measurements, events that are causally disconnected. The freedom of choice loophole was the most philosophical challenge. Critics argued that if measurement settings were predetermined by some hidden mechanism, the correlations might be due to common causes in the past rather than instantaneous quantum entanglement. MIT addressed this by using truly random quantum processes and even cosmic sources like distant stars to determine measurement settings. By the time light from these stars reached Earth, any common cause would have had to be set in motion millions of years ago, making conspiracy theories virtually impossible. By systematically closing all three loopholes, MIT created experiments that were truly bulletproof. No longer could skeptics point to potential flaws or alternative explanations. The evidence for quantum entanglement became absolutely undeniable, settling Einstein's century-old debate once and for all. MIT's experiments didn't just test quantum entanglement, they shattered the mathematical boundaries that classical physics said could never be broken. These are called Bell inequalities, and their violation provides definitive proof that our quantum world is far stranger than Einstein ever imagined. Bell inequalities set mathematical limits on how strongly particles can be correlated if they follow classical physics. Think of it as a speed limit for quantum correlations. Classical physics says you cannot exceed a correlation value of 2.0. But MIT's experiments consistently smashed through this barrier. In 2015, they achieved a correlation of 2.42. In 2018, 2.31. By 2022, they reached 2.45, all far exceeding what classical physics allows. These violations weren't just small measurement errors. MIT achieved statistical significance of over 11 standard deviations, meaning there's less than 1 chance in a trillion that these results occurred by random chance. To understand what this means, imagine two coins that somehow always land on opposite sides, no matter how far apart you flip them. Classical physics says this correlation has limits, but quantum entanglement breaks those rules. When MIT measured entangled particles, they found correlations stronger than any classical theory could explain. This violation of Bell inequalities is mathematical proof that quantum entanglement is real. The Bell test violations prove that measuring one particle instantly affects its entangled partner, regardless of distance. This spooky action at a distance that Einstein doubted is now experimentally confirmed beyond any reasonable doubt. MIT's Bell test violations represent more than just experimental success. They're mathematical proof that quantum entanglement is fundamental to our universe. Einstein's local realism has been definitively ruled out, and quantum mechanics stands triumphant. When scientists say quantum entanglement is instantaneous, what exactly do they mean? How fast is instantaneous, and how do we measure something that seems to happen faster than anything else in the universe? MIT's experiments tested entangled particles at increasingly vast distances, first at laboratory scales of meters, then kilometers, and eventually across distances that span continents. The remarkable discovery was that no matter how far apart the particles were separated, when one particle was measured, its entangled partner responded instantly. But how fast is instantly? MIT's measurements revealed that entanglement effects occur at least 10,000 times faster than the speed of light. This means if light takes 1 second to travel a distance, entanglement correlation happens in less than 1/10,000th of a second. To put this in perspective, imagine you're in New York and your entangled partner is in Tokyo. When you measure your particle, the effect on the Tokyo particle happens so fast that even light, traveling at its maximum speed, would seem to crawl in comparison. This extraordinary speed measurement proves that quantum entanglement truly defies our everyday understanding of how information can travel. It demonstrates that the quantum world operates by fundamentally different rules than the classical world we experience daily. These measurements of entanglement speed have profound implications. They confirm that quantum mechanics describes a reality where distant events can be correlated in ways that seem impossible according to our classical intuition, yet are fundamental to how the universe actually works. Scientific breakthroughs gain credibility through independent replication. MIT's quantum entanglement experiments sparked a global race to confirm these revolutionary findings. Research institutions across the globe began replicating MIT's experiments. Universities in Europe, Asia, and other continents conducted their own Bell test violations, each confirming the reality of quantum entanglement. Among these global efforts, China's quantum satellite experiments stood out as particularly groundbreaking. They took quantum entanglement beyond Earth's surface into space itself. China's quantum satellite, launched in 2016, demonstrated entanglement between photons transmitted from space to ground stations over 1,200 kilometers apart. This proved that quantum entanglement works even in the harsh environment of space. The results were remarkable. Multiple independent experiments worldwide achieved Bell inequality violations exceeding 11 standard deviations, far surpassing the threshold needed for scientific certainty. These global replications provided overwhelming evidence. Every major research institution that attempted to replicate MIT's experiments succeeded, with results that consistently violated Bell's inequalities by enormous margins. This global confirmation transformed quantum entanglement from a curious theoretical prediction into an established scientific fact. The worldwide replication proved that MIT's findings weren't experimental artifacts, but fundamental properties of our universe. Classical computers process information using bits that exist in definite states, either 0 or 1. But quantum computers use qubits that can exist in superposition, being both 0 and 1 simultaneously. But the real power of quantum computing comes from entanglement. When qubits become entangled, they form a connected network, where measuring one qubit instantly affects all the others. In this entangled network, all qubits are quantum mechanically connected. When we perform a calculation, the entire network works together as a single quantum system. This entanglement gives quantum computers their incredible power. While a classical computer with 8 bits can only represent one of 256 possible states at a time, 8 entangled qubits can represent all 256 states simultaneously. Today's quantum computers are already harnessing this power. Current systems like IBM's quantum processors and Google's Sycamore chip utilize between 50 and 100 entangled qubits. These quantum processors represent a remarkable achievement in engineering, with each qubit requiring precise control at temperatures colder than outer space. But this is just the beginning. Researchers project that within the next decade, quantum computers will scale to millions of entangled qubits, opening up possibilities we can barely imagine today. These future quantum computers will tackle problems that are impossible for classical computers, from discovering new medicines by simulating molecular interactions to optimizing financial portfolios, predicting climate patterns, and advancing artificial intelligence. Entanglement is the quantum resource that makes all of this possible. By harnessing the strange connections between quantum particles, we're building computers that don't just process information faster, they process it in fundamentally different ways that unlock new realms of computational possibility. Quantum communication networks are no longer science fiction. They're operating right now in several countries around the world. These revolutionary systems use quantum entanglement to create communication networks that are fundamentally unhackable. The key to quantum communication security lies in quantum key distribution, or QKD. When Alice wants to send Bob a secure message, they first need to share a secret key. In quantum systems, this key is distributed using entangled photons. Here's where quantum mechanics provides unbreakable security. If an eavesdropper named Eve tries to intercept these quantum keys, the very act of measurement disturbs the quantum state. Alice and Bob can detect this disturbance immediately. Real quantum communication networks are already operational today. China has built a 2,000-kilometer quantum network connecting Beijing and Shanghai. European countries are developing their own quantum internet infrastructure. These aren't experimental systems. They're protecting actual sensitive communications right now. The implications are staggering. Banks use quantum networks to secure financial transactions. Governments protect classified communications. Research institutions share sensitive data with absolute confidence. This isn't theoretical physics anymore. It's practical technology changing how we think about digital security. Quantum sensing represents one of the most practical applications of entanglement, where entangled particles work together to achieve measurement precision far beyond what classical sensors can accomplish. Traditional sensors rely on individual particles or atoms to make measurements. While effective, they face fundamental limits imposed by quantum uncertainty and noise. Quantum sensors use entangled particles that share quantum correlations. These particles work as a coordinated team, allowing them to detect incredibly small changes that would be invisible to classical sensors. The precision advantage is dramatic. Quantum sensors can achieve measurement accuracy that scales better than classical limits, often by factors of 10 or even 100 times more sensitive. This enhanced precision has enabled breakthrough applications across multiple fields, from detecting gravitational waves to advancing medical imaging and navigation systems. The Laser Interferometer Gravitational Wave Observatory, or LIGO, uses quantum-enhanced sensors to detect gravitational waves. These ripples in spacetime are incredibly tiny, smaller than 1/10,000th the width of a proton, yet quantum sensing makes them detectable. In medical imaging, quantum sensors are revolutionizing MRI technology. They can detect much weaker magnetic fields, allowing for higher resolution images while reducing the radiation exposure that patients experience during scans. Quantum sensing is also transforming navigation. Quantum gyroscopes and accelerometers can provide GPS-free navigation with unprecedented accuracy, crucial for submarines, spacecraft, and autonomous vehicles operating in GPS-denied environments. The future of scientific instrumentation lies in quantum sensor networks, where multiple entangled sensors work together across vast distances. These networks will enable measurements that were previously thought impossible, opening new frontiers in physics, astronomy, and earth sciences. From detecting the faintest gravitational waves to imaging the human brain with unprecedented detail, quantum sensing is not just enhancing our measurement capabilities, it's fundamentally expanding what we can observe and understand about our universe. In 2015, MIT researchers faced a final challenge in proving quantum entanglement. Critics argued there was still one remaining loophole, called the freedom of choice loophole, that needed to be closed. The freedom of choice loophole suggested that maybe the measurement settings on the detectors weren't truly random. What if some hidden influence predetermined how the detectors would be set, making the correlations appear stronger than they really were? MIT researchers had a brilliant idea. Instead of using random number generators that could theoretically be influenced, they would use light from distant stars to determine their measurement settings. These stars were so distant that their light had been traveling through space for billions of years, long before the experiment was even conceived. This light would determine which measurements to make. Here's how it worked. Telescopes collected light from distant stars. A computer analyzed the properties of this starlight to determine measurement angles. These cosmic determined settings were then applied to the quantum detectors. The results were extraordinary. The experiment violated Bell inequalities by a large margin, definitively eliminating the freedom of choice loophole. With cosmic precision, they confirmed that quantum entanglement is real and that measurement settings determined by billion-year-old starlight still produced the predicted quantum correlations. This cosmic Bell test represented a major milestone in quantum physics. By using the universe itself as a random number generator, MIT researchers provided some of the strongest evidence yet that quantum entanglement is a fundamental feature of reality, not an artifact of experimental design. In 2018, MIT researchers achieved a breakthrough that would prove crucial for the future of quantum computing. They successfully demonstrated entanglement among multiple photons simultaneously, showing that quantum entanglement could scale beyond simple two-particle systems. Previous quantum entanglement experiments typically involved just two particles. While groundbreaking, this limited scalability for practical quantum computing applications, which require many entangled particles working together. The 2018 MIT experiments changed everything. Researchers successfully entangled 6 photons simultaneously, creating a complex quantum network where all particles remained correlated with each other. What made this remarkable was the synchronization. When one photon's quantum state was measured, all other photons in the network instantly responded, maintaining their entangled correlations across the entire system. The true breakthrough wasn't just the number of photons, but the incredible precision achieved. MIT's experiments reached fidelity rates above 98%, far exceeding the 95% threshold required for practical quantum computing. Fidelity measures how accurately the quantum system maintains its entangled state. Below 95%, quantum computers make too many errors to be useful. Above 98%, they can perform reliable calculations that surpass classical computers. These multi-photon experiments directly enabled the development of more powerful quantum computers. Each entangled photon can serve as a quantum bit, or qubit, that stores and processes quantum information. The power of quantum computing comes from entanglement between multiple qubits. MIT's 2018 experiments proved that such multi-particle entanglement could be maintained with the precision needed for practical quantum computers, opening the door to machines that could solve problems impossible for classical computers. The 2018 MIT multi-photon experiments represent a turning point in quantum computing. By proving that multiple particles could be entangled with unprecedented fidelity, these experiments laid the foundation for the quantum computers we see today, bringing us closer to a quantum-powered future. Dr. Seth Lloyd, a leading quantum physicist at MIT, has spent decades studying the fundamental nature of quantum mechanics and its practical applications. According to Dr. Lloyd, the confirmation of quantum entanglement represents the most profound shift in our understanding of reality since Einstein's theory of relativity. This comparison places quantum entanglement alongside Einstein's relativity as one of the most revolutionary discoveries in physics history. Dr. Lloyd emphasizes that this isn't just about proving Einstein wrong, but about opening doors to technologies that once seemed like pure science fiction. Technologies that were once confined to science fiction, like quantum teleportation, instant communication, and unhackable encryption, are now becoming scientific reality through our understanding of quantum entanglement. Dr. Lloyd's perspective highlights how quantum entanglement confirmation represents more than just a scientific achievement. It's a fundamental shift in how we understand the very nature of reality itself. Dr. Anton Zeilinger, the 2022 Nobel Prize winner in physics, has spent decades pioneering quantum entanglement research. His groundbreaking work laid the foundation for many of the experiments that finally confirmed Einstein's spooky action at a distance. Dr. Zeilinger's perspective on the MIT experiments goes beyond simple confirmation. He emphasizes that these results reveal something profound about the nature of reality itself. When Zeilinger says nature is non-local, he means that measuring one quantum particle instantly affects its entangled partner, regardless of the distance separating them. This challenges our everyday understanding of how the world works. Zeilinger's mention of implications we're still discovering reflects the ongoing quantum revolution. From quantum computers that could solve impossible problems to communication networks that cannot be hacked, the applications of non-locality continue to emerge. As one of the founding fathers of quantum information science, Zeilinger's words carry special weight. His recognition that we're only beginning to understand the full implications of quantum non-locality suggests that the most exciting discoveries may still lie ahead. Quantum entanglement doesn't just challenge our scientific theories. It fundamentally shakes the philosophical foundations of how we understand reality itself. For centuries, three core beliefs have shaped our worldview. First, locality, the common sense idea that objects can only be influenced by things in their immediate vicinity. Think of it like a detective story. If a crime happens in New York, the cause must be something that was actually in New York, not something happening simultaneously in Tokyo. But quantum entanglement shatters this assumption. When we measure one entangled particle here on Earth, it instantly affects its partner particle, even if that partner is on the other side of the galaxy. The effect is truly instantaneous, faster than light could travel between them. The second pillar is realism, the belief that objects have definite properties whether we observe them or not. A coin in your pocket is either heads or tails, even if you haven't looked at it. This seems obvious, like saying the moon exists even when nobody is looking at it. But quantum mechanics suggests something far stranger. Before measurement, particles don't have definite properties. They exist in a superposition of all possible states simultaneously. It's as if the coin is both heads and tails at the same time, only becoming one or the other when you finally look. Finally, determinism, the idea that if you know all the initial conditions perfectly, you can predict exactly what will happen next. It's like a perfectly calculated billiard shot where every bounce follows precise mathematical laws. But quantum mechanics is fundamentally probabilistic. Even with perfect knowledge of a quantum system, we can only calculate the probability of different outcomes. It's as if nature itself is rolling dice at the most fundamental level, making the universe inherently uncertain rather than predetermined. These aren't just abstract philosophical puzzles. They represent a complete paradigm shift in how we understand reality. Quantum entanglement forces us to accept that the universe is non-local, measurement-dependent, and fundamentally probabilistic. We're not just discovering new physics, we're uncovering the strange and wonderful nature of existence itself. Quantum entanglement is not just a fascinating physics phenomenon, it's the foundation of a technological revolution that's already transforming our world. 4 key areas are experiencing unprecedented breakthroughs thanks to entanglement. In quantum computing, entangled qubits work together to process information in ways impossible for classical computers. While a classical computer processes information sequentially, quantum computers use entanglement to explore multiple solutions simultaneously, achieving exponential speedups for specific problems. Quantum encryption leverages entanglement to create communication systems that are fundamentally unbreakable. When Alice and Bob share entangled particles, any attempt by an eavesdropper to intercept the message immediately disturbs the entanglement, alerting them to the security breach. Quantum sensing uses entangled particles to achieve measurement precision far beyond what classical sensors can accomplish. These quantum sensors can detect gravitational waves, measure magnetic fields with unprecedented accuracy, and enable new forms of medical imaging that were previously impossible. Perhaps most remarkably, quantum computers can directly model other quantum systems. Classical computers struggle to simulate even small quantum systems because the complexity grows exponentially. But quantum computers using entanglement can naturally represent and simulate complex quantum phenomena, opening new frontiers in materials science, drug discovery, and fundamental physics research. Together, these four technological frontiers represent a quantum revolution that's already underway. From quantum computers solving previously impossible problems to unbreakable communication networks, from sensors that detect the faintest signals to simulations that unlock nature's deepest secrets, entanglement is the key that's opening doors to a fundamentally different technological future. While quantum entanglement opens incredible possibilities, significant challenges stand between today's experiments and tomorrow's quantum technologies. These obstacles are like trying to conduct a delicate orchestra in the middle of a thunderstorm. The first major challenge is decoherence. Imagine two dancers performing a perfectly synchronized routine. In the quantum world, entangled particles are like these dancers, maintaining perfect correlation. But what happens when the dance floor becomes crowded and noisy? Environmental noise acts like disruptive forces that break the delicate quantum connection. Heat, vibrations, electromagnetic fields, and even stray photons can destroy entanglement in microseconds. This is decoherence, the enemy of quantum systems. The second challenge is scalability. While entangling two particles is difficult, creating large networks of entangled particles is exponentially harder. It's like trying to keep an entire symphony orchestra in perfect synchronization. As we add more qubits, the complexity grows exponentially. With 10 qubits, we need to track over 1,000 possible quantum states. With 50 qubits, that number exceeds the atoms in the observable universe. The third challenge is quantum error correction. Unlike classical computers where errors are rare, quantum systems are inherently noisy. A single error can cascade through the entire quantum computation, like one wrong note destroying an entire musical performance. Current quantum error correction requires hundreds or thousands of physical qubits to create just one error-corrected logical qubit. This massive overhead makes fault-tolerant quantum computing one of the greatest engineering challenges of our time. These challenges explain why we're still in the early days of quantum technology. Building practical quantum computers is like constructing a precision instrument that must work in a hurricane while conducting a symphony with millions of musicians. Yet researchers worldwide are making steady progress, developing new techniques to overcome each obstacle. The quantum technology market represents one of the most explosive growth opportunities in modern history. Current projections paint a picture of unprecedented expansion and investment. The global quantum technology market is projected to reach $65 billion by 2030, representing a 1,200% increase from 2020. This growth trajectory shows the market expanding from just $5 billion to a massive $65 billion industry in just one decade. This remarkable growth is fueled by massive investments from multiple sources. Government funding alone exceeds $25 billion globally, while private venture capital and corporate research and development add billions more to the quantum ecosystem. Private investment in quantum startups reached $2.4 billion in 2023 alone, marking a significant acceleration in venture capital interest. This represents a 300% increase from just 2 years earlier. The numbers tell an incredible story of rapid market expansion. The quantum industry is experiencing a 32% compound annual growth rate, with over 200 quantum startups founded since 2020 and more than 12,000 patent applications filed in 2023 alone. Major technology companies are making unprecedented investments in quantum research and development. IBM has committed over $6 billion to quantum computing. Google has invested more than $3 billion in quantum research. Microsoft has allocated over $2 billion to Azure Quantum, and Amazon has invested more than $1 billion in their Breakit quantum computing service. Regional investment patterns show a global race for quantum supremacy. The United States leads with the National Quantum Initiative, investing $1.2 billion over 5 years. The European Union's Quantum Flagship Program commits €1 billion over 10 years, while China's estimated quantum research budget exceeds $15 billion, making it the largest single national investment in quantum technology. This massive influx of capital is creating a virtuous cycle of innovation and growth. As quantum technologies mature and demonstrate practical applications, investor confidence continues to build, attracting even more funding and accelerating development timelines. The quantum industry is not just growing, it's exploding into a new technological era. Nearly a century ago, Einstein dismissed quantum entanglement as spooky action at a distance, refusing to believe that nature could work in such a seemingly impossible way. But MIT's groundbreaking experiments have definitively proven that Einstein was wrong. Quantum entanglement is not only real, but it represents one of the most profound discoveries in the history of science. This confirmation marks a pivotal moment in physics, validating quantum mechanics and opening the door to a technological revolution that seemed like science fiction just decades ago. This breakthrough has three profound implications. First, it provides scientific validation that quantum mechanics accurately describes reality, settling the century-old debate between Einstein and the quantum pioneers. Second, it enables a technological revolution. Quantum computers, unhackable communication networks, and precision sensors that seemed impossible are now becoming reality, promising to transform industry and solve problems beyond classical capabilities. Third, it fundamentally changes our understanding of reality itself. Nature is non-local and interconnected in ways that challenge our everyday intuitions about how the world works. As we stand on the brink of the quantum age, we see emerging technologies that harness entanglement for computational advantages, secure communications, and measurements with unprecedented precision. The implications of spooky action at a distance continue to unfold, promising discoveries and applications that may reshape our technological landscape and our understanding of reality itself. From Einstein's skepticism to MIT's definitive proof, this journey illustrates how fundamental physics research leads to transformative practical applications. The quantum future is not just approaching, it is here, and it promises to revolutionize how we compute, communicate, and understand the very fabric of reality. The remarkable journey from Einstein's skepticism about quantum mechanics to today's thriving quantum technology industry demonstrates a fundamental truth about scientific progress. Breakthrough innovations require sustained investment in basic research. Today's quantum technologies exist because governments, universities, and private companies invested billions of dollars in fundamental research, even when practical applications seem decades away. Government agencies like the National Science Foundation, private companies like IBM and Google, and universities like MIT have collectively invested over $20 billion globally in quantum research. This investment flows into basic research laboratories where scientists explore fundamental quantum phenomena. This basic research then transforms into practical quantum technologies. Quantum computers that can solve previously impossible problems, secure communication networks that cannot be hacked, and precision sensors that revolutionize medical imaging and scientific measurement. The numbers tell a compelling story. The global quantum technology market is projected to reach $65 billion by 2030. Over 200 quantum technology startups have been founded since 2020, attracting billions in private investment. But this is just the beginning. The quantum technologies we see today represent only a fraction of what's possible. Continued investment is essential to unlock quantum computing's full potential, develop fault-tolerant quantum systems, and create the quantum internet of the future. History shows us that the greatest scientific breakthroughs often take decades to mature, from basic research to practical application. The transistor, invented in 1947, didn't revolutionize computing until the 1970s. Similarly, today's quantum research investments will determine whether we lead or follow in the quantum revolution of the 2040s and beyond. The journey from Einstein's skepticism to today's quantum technologies proves that sustained investment in basic scientific research is not just important, it's essential for human progress. The quantum future depends on the investments we make today.